Angela Bassa. I do data things at Enernoc, and I'm going to be talking with you guys today about how to deploy machine learning into a production environment and how to integrate that with the software stack that you may have already in deployment. So I'm going to transfer to the slides now. And so here we go. So I'm not sure if I can confirm that you guys are seeing my screen. So I'm going to start presenting, and then we'll hear back from the conference team if I have to do anything with my screen. So today I'm going to give you guys a brief introduction into what it is that Enernoc does and what I do there. Then I'm going to give you a few learnings that we've had about deploying machine learning into production. I'll also give a couple of examples that illustrate what I'm talking about, and then I'll open up for questions and we'll wrap up. So let's get started. I'm Angela. You can find me on Twitter at AngBassa if you want to engage over there after the conference. I run data science at Enernoc, where we do anomaly detection, machine learning, and all sorts of good stuff to our data. And the point of doing all of that is to change the way that the world is using their energy with energy management and help with procurement, demand response, all sorts of interesting things. So a quick introduction to Enernoc, in case you haven't heard about what it is that we do. We are a company that offers demand response capabilities. So we have our own hardware that we install at different sites all across the globe. And we help those sites manage situations where there might be an energy crunch, a supply crunch, things that usually tend to lead to brownouts and blackouts. We help the grid avoid that kind of development. And we do that based on some software that we have written both for our internal professional services team that deploys our demand response dispatches and does sorts of other things like procuring the best energy across different providers. But we also offer that to end users, to commercial and industrial customers who may be interested in managing more closely their own expenditure on utilities, either because of sustainability efforts or because it just makes sense to not waste money in energy. So a few stats about Enernoc. We have sub 2-second response time for over 3,000 peak users per hour. When we talk about reliability, we're talking about 99.99% availability for critical apps. These are the apps that don't happen in batch, so that they're available every 24 hours or whatever frequency. We also offer a global architecture. So our apps are localized to, I think it's scores of countries, and they're localized where the deployable applications are, they're localized to 15 countries. So the end user version of energy intelligence software is much larger than this, but the critical applications are localized really quite broadly. When we talk about a scalability, we're talking about 150,000 new data streams expected by the end of this year and 8 terabytes of new monthly data by 2017. So we're not talking about crazy scale that the largest retail players in the space reach, but it is quite sizable. We also have to offer instantaneous access to the insights because these are activities that need to take place under stress with the grid. So there's real-time streaming customer data that has to be available in near real time. And we have a DevOps mentality of rapid development of new applications so that once we have iterative developments taking place, they can be deployed efficiently without having any downstream implications. So this is a little bit about Enernoc. Let me just escape real quick and check that there aren't any messages and that everything is good. Awesome. All right, let's go back. So you guys have probably seen this cartoon. It's one of my favorites. What we do here at NRNOC in terms of, or which data we use in order to be able to reach all of these different insights is really quite multifaceted. We don't have simple features that we work with, and we also don't have data that we can very readily believe. The canonical data is the data that comes from the utility providers, but we don't always have instantaneous access to that. So we have information from our demand response meters, from energy consumption that we have either via our partners or via the utility providers. We have weather forecasts and weather historicals. We have monthly bill information that we can try to triangulate from, and we have less now utility providers than we used to have, but we have a sizable presence in the utility space as well. So we get all of this data coming from all these myriad places, and we triangulate to try to find what the true information is at any given time, which is what we ultimately end up showing to our customers via our application, which is both mobile and connectable to the large building management systems, the BMSs, the JASes, that connect straight into large industrial facilities. So getting a little bit deeper into how it is that we deploy machine learning in a production space of this type of scale. I love this particular little cartoon from The Godfather. It's not personal, but it's also not academic. So it's a business, and it's a business where we're only going to be able to eat what we kill. So it has to be resilient at a scale that isn't necessarily the same kind of scale that you publish on, but it's the scale that if you go down, then suddenly maybe an entire portion of a grid, of an electrical grid, isn't able to withstand some kind of supply crunch. So this is a different proposition than one that is more driven towards an academic pursuit of optimization in the machine learning space. So what we do at NRNOC is that we have this mentality of uniting research and development. These can be very separate things. Usually they are very separate things in many different companies, and at NRNOC they were very separate. So at NRNOC, when we were talking about development, we had this sort of construction contractor mentality of knowledge being used to design a blueprint to construct these programs that meet these particular specifications, either from product management or from contractually from our partners in demand response. And for anybody who's done a little bit of machine learning, you guys are probably aware, knowledge is actually used in a different way than it is used in development. We have these activities that we do. We plant the seed where we have this algorithm that we're applying. We feed it with we give it feed, we give it water, which is the data that we're giving it, and it can contain all sorts of anomalies or biases. And then we reap the plants in the programs. Which is to say, you can't really promise, even after you plant it and you water it and you feed it, that the tomato is ever going to sprout, that your program is ever going to deliver in a way that is the way that most development environments are expecting it to happen in. So what you end up having is something on the left. You can see the rural environment is separate from the urban environment. You have the developers in the background and your machine learning data scientists in the foreground, and everybody hates each other. The people in the farm think that the city is polluting their visual environment, and the people in the city are going, why can't you just give us a space to build more buildings on? And nobody's happy. So what we're trying to do is displayed on the right-hand side, where we're trying to have something that's truly symbiotic from its very inception, where we are having these farms that are built within the urban environment by design and from the get-go. So hopefully we have a little bit more integration so that it's a little less painful to transport things from one side of the operation to the other. Now, granted, mistakes were made in these types of implementation. It isn't easy to put these two very different environments together. And so I'm not going to discuss too much about the things that went wrong, although if at some point we meet in a non-online conference, we can catch some coffee and I can tell you more about it. But what I will tell you guys is that I'm not the first one to notice that things can go very wrong. Josh Wills gave a keynote at the Data Engineering Conference in San Francisco this year, where he introduced, and if you know Josh Wills, you know the big red foam cowboy hat. And he introduced this concept of this infinite loop of sadness, where you have your data engineers who have unrealistic expectations of their data science team, who have unrealistic expectations of the business, who then have unrealistic expectations of what ops can deliver, who have unrealistic expectations of what data engineering can help them with, and vice versa. And lots of companies get stuck in this infinite loop of sadness, which is sort of, data science. What is that? Is that like complicated SQL? Great. So what do you want to do with that neural network? And is it working? How can you check for me? I mean, it can get pretty out of hand because the different corners of this loop don't really understand the vernacular used in the other. And a lot of things get lost in translation. So how do we fix the infinite loop of sadness? We fix it with the love. And the love is made of 5 different parts. And this is the finding that we have had in our team, is that you need to have acceptance criteria by all parties. And these have to be pretty rigid and transparent and using the vernacular that all different parties understand. So everybody's on the same page. Having meta cost functions is also really helpful. Using the right tool for the job, depending on what the job is, rather than fitting the job to the tool. Having golden data sets and a testing harness. And I'm going to go into detail about what all of these mean. So let's talk about a couple of examples where I can let you guys know what the love looks like in real life. So I'm going to talk about 2 things. One is I'll discuss this flagship product feature that we have in our software. So that the customers are really happy when it works is sort of the mentality. And the second one is something that happens under the hood. So we're going to talk about anomaly detection and handling. And in here, customers are really upset when it doesn't work. So where the benefit to the customer and how we hear that message translated is very different among these 2. So let's start with the novel product feature. What I'm going to talk about here is this feature we call weather normalization. This is something that is really well understood in the industry. So if you want to compare buildings in your portfolio across time and space, let's say you have one building in Australia and another building in the UK, and you want to see how they are, how could you compare and contrast their energy consumption? But the problem is in the Southern Hemisphere, it's going to be winter, when in the Northern Hemisphere is summer. So if you're going to compare the usage of these buildings in January, well, one is heating the building, probably using something like gas, whereas the other is cooling the building using something like electric. And those are going to have very different profiles in terms of how they rate, how much of each you need in order to achieve the temperature that you want given some external temperature. So we developed something algorithmically that delivers much more granularity than the daily industry standard, which means we now can normalize hour by hour of buildings across time and across space. So more formally, what the business came to us with was they wanted us to build a cloud-based application so that it wouldn't be held in on-site, that would allow for apples-to-apples comparisons of energy consumption across locations, timeframes, building types, all sorts of different metrics in a daily batch transformation that had an hourly resolution. Now, let me explain the colors. Before, when I showed you the Venn diagram of research and development, I used the amber and blue colors to shade the different sides of that, and the intersection was green. So here, the problems are being able to deploy in a cloud-based fashion. That's an engineering problem. That's much more towards the development end of the spectrum. Whereas allowing for an apples-to-apples comparison of these buildings algorithmically, that's a research question. And bringing it to an hourly resolution where the industry standard had been daily up to now is also a research question, whereas the manner in which you make these calculations available to the customer is a development problem. So that's why cloud-based and batched are in blue, apples to apples and hourly are in amber. So let's talk about what the acceptance criteria, the first piece of love that we have and what that looked like. So for weather normalization, the typical calculation that ASHRAE engineers perform, and ASHRAE is the industry society of engineers who perform these energy analyses. They know when it looks right. So similar days are supposed to have similar values. Hot days are supposed to display a discount versus cold days. They have these heuristics already. So it was very important that whenever we showed something that was this novel model that we had, did not cause anybody who had 30 years experience looking at what this looks like to recoil. The second criteria that we had was a practical implementation, since normalized data series would be calculated from very large native interval data sets. So this had to be something that wouldn't bring the whole entire stack to a crawl every time this particular batched calculation took place. And the third thing was, we can't very well sell this to customers and ask them to wait 3 months until they have some data that they can use and charge them for those 3 months of data accumulation. So it had to be actionable with very limited data training. So even though these large native interval data sets are large because we're getting information at the 5-minute or 15-minute resolution, so even just a week's worth of data starts getting really big for large enough portfolios. We wanted to be able to train this quickly so that the customer got value immediately, or as close to immediately as possible. So we all agreed that those were the main acceptance criteria, and that allowed us to make prioritization questions, to have prioritization discussions, because we all had agreed on what the top line table stakes were. So the second piece of the love is what I call the meta cost function. So usually when we're talking machine learning, we have the mathematical cost function, which is something that you're trying to optimize your model to. So you're doing your bias variance trade-off. You're talking about cross-validation or design optimization. You have your L2 norms for your linear models, or you're maximizing margins for your SVMs. So all of that is the model part of the cost function, but there's the business part of the cost function, where you're also optimizing for different variables than necessarily the specific machine learning variables, which are computational costs. So how much is it going how much is AWS going to charge us, or model explainability? This is a big concern, especially in the academic world. But if I can't explain to my marketing peers or my sales team or my customers what it is that my model is doing and how is it that is going to be valuable for them, so that they can explain to their management line why it is that they're spending money on this software, that's very important. The product requirements, what are the latency requirements, what is the UX going to feel like, and also data availability. If we don't have enough data in our data sets to train these models and validate them on, then how valuable is it to spend development time on any of this? And what's the opportunity cost of not putting those scientists, researchers, and developers into a different product, And also architectural complexity, because the more I need to rely on different teams across our engineering organization, then the harder it is going to be to maintain this sucker once it's actually deployed into production. So this is what I mean when I'm talking about the meta cost function. In terms of a golden data set, this is pretty much obvious in hindsight, but I've seen a lot of production environments that don't employ this. What I mean by this is you have an input and an output that worked in the research environment. And so we call that the golden data set. We separate the input from the output, and we give the input to our development team, who is going to build a machine that is some function of the thing that we build, plus some error. And what we're trying to ensure is that their error is minimal, or it is in a dimension that we don't care about. And so they have some output, which then we compare to our golden output. And we can ensure that their production stack or their production implementation of our research is perfect. And so far, we can do these kinds of things to get to the level of machine precision or machine error in between the stacks. And the way that we test it is by having a testing harness that is part of the development process and not an afterthought, and it's not something that we lob over the wall to the QA team. So what they're doing in that case is they are building several variations of their implementation that are slightly perturbed in some way, either by taking in the data out of order or taking in the data with large gaps and ensuring the resiliency of their implementation. And that's on the left-hand side. On the right-hand side, I have a similar sort of concept, but where not only the perturbations are present, but the perturbations are out of order. So you're really trying to jig the system to make sure that it withstands all sorts of different data cases that might be coming into it. So we use both errors and weirdness that we found in our data set to begin with, but we also have a synthetic, quote unquote, crazy data set that we feed into this to make sure that the output is never going to either blow up into infinity or do something crazy that will cause our stack to become less resilient. So before I tell you guys how it is that we implemented this, I just want to make sure that you understand that this is just one way to get this done. There are certainly many different ways of making that product request, that the problem definition be available to an end customer. So our version looks this way. The research was done in Mathematica. And the reason for that is it's really difficult to hire unicorns. And especially when the likes of Google and Amazon are so very attractive for the unicorns. So the talent that we had in-house that had the availability to study this and who had the passion to take it to a point where we've been able to file about 10 patents on this particular novel implementation of weather normalization, what he knew really well was Mathematica. So what we did is, rather than fit the product to the tools, we fit the tools that we had at hand to the product. And so we had to have this translational step in Scala, could happen in any JVM, I suppose. And then at that point, what we were testing was a Kafka Spark implementation for the queuing and the processing, which worked really well for this particular job. And so here's just an example of what it looks like. If you had a login, if you were a customer and you went to look at your office building number 5 and your second multimeter, if you looked at a month ago versus the week before that, so August 28th versus the week of August 21st, this is what the data actually looks like. But if you turn on the toggle for the weather normalization, you can see that whereas before you thought maybe your building was spending 7% more energy this week compared to last week, when you account for the fact that the weather was quite different, the building was actually only spending 2 percentage points more energy. So it's not quite as less efficient this week than it might otherwise have seemed had this calculation not taken place. So that's the first example. Let me escape out of this real quick and go back here to see if there are any questions so far. You guys good? Oh, here we go. So energy, somebody, Piyush Vaish, and I'm sorry if I mispronounced your name, asks, energy is a very traditional industry with lots of legacy systems. How do you try to keep up to date with integrating learning from the data? Does it help the regulated and deregulated energy market as a whole? Energy is a very traditional industry, and one of the concerns that they have with trying new things is that it may cause an imbalance in the system and take down and take the grid down with it, which isn't really nice. So part of what we're trying to do is we're trying to use these novel learnings, which aren't part of the critical path for any of these customers, so that they don't have to worry about any of their systems becoming compromised by utilizing these new tools. But you're absolutely right, and that's a huge uphill climb that we have. All right, so that was a feature. Let me talk about under the hood, which sort of goes a little bit more to what Piyush, you're asking about. So let me go back to the slides. So let's talk about anomaly detection. Anomaly detection is something that we use to ensure the quality of the data that we provide, either to alerting or profiling, or the weather normalization feature that I just mentioned to you guys. So going back to the question, here's the thing about reliability, and here's the thing about the energy industry. If you have a bridge that covers your backyard pond, and by the way, if you have a backyard pond, good job, doing really good. But if that little bridge breaks, then you can just hop over the pond and no harm, no foul, and you'll call your landscaper eventually, because if you have a little pond, you have a landscaper, and I want to be like that when I grow up. But on the right-hand side, what we have is the George Washington Bridge in Western Manhattan. And if that goes down, pretty much all of Western Manhattan goes down. Nobody who commutes in or out of the city can get anywhere, and the city will grind to a halt. And so when we're talking about implementing these machine learning systems into the production stack, our production stack is on the right-hand side. And that's something that causes a lot of trepidation among our customers. And so we have to ensure that the data that we're giving them is of the best quality possible. And the problem with that is data quality is not something that is scalable unless you start applying algorithmic or heuristic rules to the anomaly detection. There aren't enough eyeballs to look through all of the 5-minute intervals that are coming through to our system, and it has to work. So here's what we use in the industry. There's this process called VEE, which stands for verification, editing, and estimation. So what we get is a time series like what's on the left, the before pane. We get data that has missing pieces. It spikes up, or you have these drops that are not supposed to be there, because we know from physics that that's not how energy behaves. So this is something that wouldn't really be possible unless something really funky was going on, which we would be seeing from radar or satellite. So this is really just a problem on that data. So we verify all of the intervals to make sure that they are correct. Several here are not. Then we edit out the bits that the spikes, the spike drops and drops. And then we estimate over the gaps. So on the right-hand side, you can see that the spike, the drop, and the gap are all filled in with blue, which is the part of this algorithm that's a little bit different is generative, because you have to infer what the consumption would have done otherwise. So more formally, we need reliable data to underpin all of the downstream analytics that we have on our platform, and to run on all of our incoming time series with minimum latency and in near real-time performance. So back to the convention that we are working with, the amber colors are a little bit more on the research side, and the blue colors are more on the development side. But all of this was required to be able to deploy VEE on our data streams. So here, the acceptance criteria are a little bit different. It had to be supportable by our production operations team, who is sort of our application support team, whenever there was an issue. So this thing would not scale if you had to call an expert at 2 a.m. whenever it fell. And the thing about providing 99.99% reliability to critical applications is that that's exactly what happens. We have people who, back in the day, used to have pagers. Now they just have iPhones or whatever device they want. But it has to be supportable by that team. The second piece is the data handling had to be very conservative. So in industry terms, when you have a regulatory body that's looking at the data that you are presenting either as causal to some kind of activity, what's going on there is that if you attribute to your activity, the corporation selling something, if you say you're responsible for something happening that you actually turns out aren't, that's a false positive, but the industry looks at that as fraud. Whereas if you say, oh, we are not responsible for all of this wonderful activity, that's a false negative. And at that point, ENERNOC is not make money. So both are bad, but one opens up to all sorts of regulatory liability. So the conservative portion of the data handling was very important. And the third piece was these rigid service level contracts, so that if production operations at 2 a.m. ever has anything that they need to escalate, they need to be able to know who to escalate very quickly. So the same things apply here. We have a meta cost function where we took into account how much it would cost to deploy all of our data streams going through this in the cloud, which is part of the move that we are making of our systems to the cloud. So all of the same questions also apply. We also had several golden data sets that we fed into our version and their version of the algorithm. And we also had perturbed testing harnesses. So the pain points that we faced here are a little bit more generic, than in the feature, because we had to do a lot more ETLing to get the data around. So in Spark, you have a simple abstract stream that you write your data science code around. So you never really know about the detail of whether if it came from an AWS stream or if it came from a distributed file or whatever. You don't have access to that information. Whereas here, we were going to need to have access to that information. So the stack looks a little bit different. And here's the stack that we went with. So we used R to develop, because we could instantiate little pieces of R into our Lambda boxes, so that the algorithms here being much more complicated and being much more nested into each other for the specific data handling that we were required to perform. We went with R rather than Mathematica, which is not something that you can easily just use a library and integrate. We also had that translational component, and that's our talent is in Scala, so no reason to mess with that. But you'll notice that the lower part of the stack looks very different, and that's because in between the first project and the second project, as Enernoc was doing its investigation outside of the data science team, its investigation into what the stack was going to look like from a foundational standpoint across our cloud migration, they settled with Kinesis and Lambda. And so all of the learning that we had building a Kafka Spark world had to be applied. And it turns out that because we had modularized everything the way that we did, it was actually a very similar proposition to translate from one statistical language to the production stack, using a data engineer who was fluent on both ends to write that glue in Scala, or really any JVM would work. So one more thing before I close is that we are now in the process of migrating weather normalization from the old stack that I showed you guys to this new stack. And because of the rigid contracts and the modularized way that we built this, it's actually been quite simple to sever the ties that we had with the previous layer and reintegrate it into the new layer. And it actually took us about 4 weeks of one person on our team to make the migration. So highly recommended, because from a manager's standpoint, upkeep and keeping up with the rest of the organization's decisions has turned out to be really much easier. And these kinds of problems are not the kind of thing that you face in academia, but when you have to have an airplane flying that needs fixing and you can't land it to perform the fix, which is normally what happens in our resilient world, that's quite a nice feature to have. So just in closing, you can't pass the buck because the buck doesn't pass the acceptance criteria. So the only way to do that is to have the buck live in the same place as everybody else's buck. So that's my presentation. I went a little fast to make sure that we stayed under the 40 minutes. So I'm going to open up to a few more questions. Let me go back. Hello. All right. Oh, we do have a question from Daver. I'm sorry, I'm mispronouncing your name. He asks, sometimes the tools, both mathematical and otherwise, are very different between the dev team and the data team. Yep. They use MatLab and Python for data, and the dev team uses Scala Spark. So the translation seems to be a huge bottleneck because of the mathematical literacy, the programming styles. Yep. So this is where the golden data set has really saved us, because our dev team also lacks in I mean, they're very they're very good at math, but they also have a self-selection where they didn't go to school for math because they don't have that passion, and what they did is development. So by ensuring that they didn't have to understand exactly what was going on, mathematically speaking, just mathematically speaking, in their translational step, by having these tools that allow us to compare down to machine precision, they were able to become they were able to reach comfort that their implementation, their translation of our research had actually not been ruined by some introduction of bias of some kind. So that's the part that really worked for us. Do we have an interface between the two? We don't have an interface because they live together. So our team actually has a data developer, data analyst, a data engineer, and a couple of data scientists all working together on the same project. So there was no wall to lob over, which is something that I would recommend for anything that requires this level of resiliency. Oh, sorry, Piyush, you had a second question. Oh, no, I think I answered that question. Is that another one? Yep, Eric, thanks. So do you have any other questions? All right, well, I hope that this has been helpful for you to see one way that we have been able to deploy complex algorithmic systems and machine learning systems that are really valuable to our customers in a way that that allows them to trust the results that they're getting. Thanks, Noemi. And Isaiah as well. You guys are really nice. Thank you. Oh, I did get one quick question, so I'll answer that. But if you guys need a quick bio break of 3 minutes before the next talk, thanks so much. And I'll just take questions now until they seem to dry out. So you're welcome, Davor. So Eric, you ask, did I say the main solution for dev versus data team was for the data team to provide examples of their inferences? Yes, so not just examples of the inferences, but what we did is we had a set of inputs and a set of results that were completely divorced of how we got to them. So it's, in one incarnation, it was a giant JSON file that you could just pipe into the development system, and it would, and through the testing harness that we built to be able to enable. So this testing harness that we built, you can, it works almost like an API where you can connect the data feed into it from our golden data set, and you can connect the application that we are testing, and it will perform all of the perturbations. So it will feed it data from the golden data set in weird chunks in backwards order with bits missing, and then it will compare what the output looks like. And if the algorithm is correctly implemented, no matter what you do to the way that the data is input into this new application that we've developed, the output will have to match the thing that the research team had originally. And so by providing those two things, the testing harness to the development team, which will do things to their code in the same way that it does to our code, and feeding them the raw input, they can compare their output to ours. And then we can make sure that even if we don't understand their implementation and they don't understand our math, and I'm speaking in the us versus them, but it's all one team. And I'm sorry if that created the confusion. Does that answer your question, Eric? Awesome. Oh, Davor has another question. So what are the most interesting math concepts that I learned in or out of school that have changed the way I go about solving a problem? That's a great question. I will say that the most ubiquitous method that I use is the regression, which isn't very sexy, but it does work very well because a lot of the things that you can apply it to are going to be multidimensional anyway. So unless you need to reach a level of precision that accounts for the multiple factors that are drivers to whatever it is that you're trying to predict or infer on. Unless you have to have that level of precision, a linear regression or a two-dimensional regression usually will do the trick just fine. The thing that I have learned that has helped me more than anything, rather than specifically which kinds of methods, but how to apply the methods. So it's really important whenever you get a new problem to try to solve it the easiest way possible. And seeing if the easiest way possible doesn't work, what about it doesn't work, and then just adding complexity ever so slightly to every single layer, rather than starting out by doing a convolution right off the bat. If you're dealing with meaty enough problems, you'll eventually get to the convolutional fun, but it's very difficult. I mean, I think we employ a really complex algorithm. Maybe like every other month is when one of those attempts is fruitful. More often than not, we're really trying to figure out what is it about the simple solution that hasn't worked so well, so that we can tweak it just there, so that we're just tweaking parameters. Because for us, perhaps differently than many of the other speakers, but for us, model explainability is a huge piece of being able to sell these solutions. Oh, work in progress asks. You're welcome, Daver. Just to get some clarification on the testing harness to match inferences, what part of the tech stack that you mentioned is that it's built in Scala. And the whole thing is Dockerized. So that's why we can just take our piece out, put the developer's piece in, and run through the whole system. And we deploy all of those things into the testing harness with Jenkins and all of that good stuff. Just regular production stack. Although, I forget you guys don't live inside my head, so sorry. Not regular production stack. Our regular production stack at NRock. All right, you're welcome. Everyone, thanks so much for watching. I'd love to hear what you thought about it. So either let me know through this platform, let me know on Twitter, and I hope it was helpful. Bye, guys.